thanks a lot for the kind introduction and to the organizers for the invitation to this really amazing event. So I'm very happy to be here. And and we've seen so many very interesting applications so far. And so my presentation will be a little bit more technical. So I still hope that it will be maybe somehow interesting. And so as already mentioned, and as the title is, so I'm really lately very interested in deep learning for neurotechnology. And so one obvious motivation for that is, of course, the huge success of this class of machine learning methods in other domains like computer vision and natural language processing. And basically, I think most here will be familiar with the concept that was already mentioned several times in the preceding talks. And what we're talking about is a class of machine learning based on artificial neural networks that are arranged in what I can use this here, which are arranged in many layers, and because there are many layers, it's called like deep. Yeah, this is the basic concept, and of course for these really interesting and also clinical relevant applications that we've seen so far, I think in many situations it would be great to get more information from the brain signals, and this is like a basic motivation for us to look into this method. However, deep networks are also like infamous for the fact that they can be quite a black box, and in many, especially safety critical medical applications, this is not what we really could accept. So this is another topic to talk about. Can we actually understand what these methods learn from the data? And just as a little bit of background also about if we now talk about decoding information from brain signals, so where can we look for that? And so they are now very simplistic. So there are two features that are often informative. There are definitely many more, but two are very well known. And this is one is there are modulations of the amplitude of oscillations, like here in my hand drawing here, the upper example. And the second basic mechanism is changes in the signal phase, which could occur independently of amplitude modulations across channels or frequency bands. So this will be important for the remaining talks. So this is two very well-known sources of information, and with classical machine learning, you would also pick different processing pipelines depending on where you would suspect the information to be represented. And when we started looking into deep learning, the landscape was kind of this. So here, this is meant as a schematic of an kind of design space of deep networks. And of course, there are many parameters that you can adjust in networks, like the number of layers, the number of filters. So it's actually a quite, of course, high-dimensional space. And across this space, there were many networks that have been proposed, and here I try to draw them with these little symbols and scaling them. The small ones are meant to represent studies that applied deep networks, let's say, to one data set, and others maybe looked at two or so, but not really very many in most of the cases. And some of these examples would fall in the category of data sets where more the amplitude was informative, or the phase, like, and this is meant to be the squares and circles. And then now starting to work on this, our idea was somehow not now to, of course it's tempting and it's really interesting to try out many different architectures, and so, but what we wanted to do is actually to concentrate more on one architecture, but apply it to many different data sets. And especially we wanted to apply our architectures to both scenarios that I described, so to data sets where we would think that the information is in the amplitude part, and to data sets where we would suspect that it is in the phase part. And to do this, we kind of wanted to design something like a prototypical network where we wanted to have enough capacity so it could learn the typical sized data sets that we have, but on the other hand, we didn't want to make it unnecessarily complicated. And we thought that this would be then hopefully a good starting point also to try to figure out what happens inside these networks once they are trained. And so this is the network after quite a while trying out many options that we came up with and that we have described in a paper in 2017 in Human Brain Mapping. And just really briefly, the idea is to have in the first layers, like here, a filter over all electrode positions, so a spatial filter, and then in the remaining layers, a hierarchy of temporal filters that would be by design able to extract something like hierarchical temporal information from the data. And we also made this publicly available in a toolbox together with the data. If in case you're interested, we're really happy if this is used. And actually, in the meanwhile, it's really used in quite a number of labs worldwide, and we are really happy about that. And now applying it to first, we choose an typical example, like also in some of the previous presentations, where the modulation of spectral amplitude is a well-known source of information, and this is decoding of movement classes like hand versus foot movement. And so we did that from EEG data, and here you see the accuracy of our deep network against filter bank spatial patterns, and it was, let's say, at least as good and even statistically a little bit better than this comparison. But the main point here for us was that we trained the networks really on the raw data. So we didn't make any a priori decision that we wanted to look at spectral amplitudes. This is just what the networks learned. So next, we looked at a counterexample where we would I think that the information is more in the phase, and this is error decoding, was also mentioned before. So a paradigm where you have to make a decision task under time pressure, and there you get this typical ERN-like response, and there it's more the phase which is informative, and so filter bank spatial pattern wouldn't work well here. But again, comparing deep networks to our RLDA as our baseline here, it performed quite well. So, and then third example that I want to give to you is here. This is now an already more useful example. So this is decoding pathology from clinical EEG, just to say from an recording in a patient, whether the clinicians said it was the patient had signs of an underlying pathology, and so binary classification, and based on a really large public data set from the Temple University. And this is a situation where it would be really hard to say, so where would you look for the information in this case? So it could definitely be in the amplitude of some oscillatory components, or it could be in the phase, or both. So, and here with, and here's an example what you get if you look at all features from the literatures. We ended up with like 9,000 different features that you could look at. And then again, but training now these networks on the raw data, we got 86% accuracy, which was significantly better than the baseline. So we could increase the state of the art also in this task. And we were also really happy that another group picked up our architecture and applied it on a different clinical data set here, and achieving very similar accuracy, which is kind of a nice external validation, I think, of our method. And then, as I mentioned before, we also wanted to apply our networks online, and this now for time reasons. As it doesn't work anyhow. So this would be a movie, but actually we also have it on YouTube, which would show an online application of our networks, and there we controlled a robot using an adaptive version of these networks and achieved significant control. So this is then like I think more like an engineering problem, but at least we could show that one can get good online decoding accuracy with the same approach. So, okay, now here it is. So but I think I'll skip it just because it's getting too late as well. Okay, so but I think this first part anyhow was just to show that we now have an yeah, I think a prototypical deep network where we can show that it works across a large number of tasks, both from healthy subjects and from clinical populations. And now we wanted to start to look into the internal representations of what do these networks actually learn from the data. And now one very famous result from the computer vision deep learning literature is shown here. So this is a paper already from 2012 and 13, where you can see that neurons in the early layers tend to maximally respond to simple geometric features like edges, while in the higher levels you might find neurons which are only interested in something like faces, for example. So this is this famous idea that there is a hierarchical organization of more and more complex features that is learned by the networks, although if you look in the current literature, this is really a very active and controversial area of research, what is really learned by these networks. But starting from this, we first did a very simple analysis of what are the maximally activating inputs in our case. And so here, each quadrant is one layer, so from input to output. And if you, for example, if you would look here, this is an early layer. Many of the units or neurons maximally responded to what really looks like a sinusoidal oscillation. And while in later layers, for example, here in layer 4, there were neurons which were only interested in oscillations that would grow in amplitude and not at all in oscillations that would stay the same or diminish. And so this is maybe a similar phenomenon like these more and more complex visual features that I just described. Then, however, to go on from there, of course, if you look in the deep learning literature, there's a huge amount of, or there's let's say there are many really good deep learning specific methods to look into networks like I've listed here, so saliency maps, deconvnet, guided backpropagation, or pattern net and attribution net from Klaus Robert Müller's group. But before, and we are really interested in trying this out. So for example, we have just finished a PyTorch implementation of PatternNet, which is also now part of our Brain Decode toolbox, if you are interested in that. And but to start, we did something much more simple. So we, because we wanted to do hypothesis testing, we just perturbed certain features of the input, like amplitude features or phase features, and looked at the impact of these perturbations on the network output at different network layers. And so this allowed us to test whether and how these amplitude and phase features are actually represented in the networks. And this is now also from our 2017 paper where we applied this method. And here the rows are different frequency bands. So on top is alpha perturbations of the alpha power, and each map is like the electrode layout. And what you can see here is that decreasing the alpha power above right motor cortex made the networks think that it was a left-hand movement, like this would be here. And this, of course, makes a lot or perfectly sense with respect to what we know about the typical physiological modulations of alpha by hand movement. And if we go now to the high gamma range, we observed exactly the opposite pattern, which, of course, again, is exactly what you would expect from the known physiological responses in motor cortex. So we were really happy to see that. And this was also, as far as I know, the first time that this had been shown that these networks really learn very interpretable spectral power changes without having any kind of inbuilt mechanism to actually learning power. So there's no squaring function or something like that in the networks. So then we applied the same method to the pathology decoding task that I talked about earlier. And again, looking at the spectral power modulation in different frequency bands, first of all, what we observed, and you can see this here on the left, was that increasing the low frequency power above the temporal cortex made the networks think that it was a pathological example. And this, of course, again makes a lot of sense because temporal slowing is like the most universal, unspecific index of EEG pathology that is also used by clinicians. However, then also looking into the higher frequencies, if you look here at the very right, you see this bluish map, and this indicates that in addition to these low frequency changes, the networks also used reduction and especially diffuse reduction in high frequency power to make this, to judge an EEG example as pathological. And this, of course, is something that clinicians cannot or do not use. And this was for us, therefore, an interesting example that by analyzing what deep networks learn, we found something that we didn't expect and that we can now further investigate and look for the meaning of this pathology-related decrease in high-frequency content. So then to take this even a step further, we went to intracranial EEG. This has already mentioned several of the talks before, so I think I don't have to explain this ECOD method in detail. And here we looked at now not decoding of movement classes, but of actually doing regression to decode really kinematic parameters like speed, velocity, position, and so forth. And from our previous work on this data set, and this is actually like you can see on the top left, it's a little car driving game. We know that in this task, decoding of different movement parameters in one and the same data set involves information either in amplitude or phase features, which is for us a very nice situation because we can now look at this in much more detail. Now this is a very busy slide, but actually it's just to give you an impression of where we can go now. So this is actually now each column here. Let me show you. Each column is a layer from 1 to 4. And each row, sorry, and the columns are the different movement parameters. And now, and blue and red are motor and non-motor channels. And now, if you look at the red curves, one can beautifully see how, with increasing depth, the output of the layers in the networks develops this sensitivity to spectral features in very meaningful frequency bands like beta band, power, and it's always amplitude phase, or low frequency phase. And this makes, again, a lot of sense from the known physiology, but now we can really see how these patterns emerge within a network, and interestingly, also different patterns for different movement parameters just based on the same data training for these different parameters. And now, as a next step, so it's again the same basic arrangement. So the rows are the layers and the columns are the different movement parameters. And now we just made a histogram by plotting this, by plotting the amplitude versus the phase sensitivity for all units. And so and we encoded the preference of the units by these colored bars. So a vertical bar would indicate a purely phase sensitive bin in this histogram, while a horizontal one would be a purely amplitude sensitive bin. And what you can see here is that in the middle layers, we still get this mixed case. So red would be units which are tuned to both, while at the end, we do not get this anymore. And so this is for, let's say, in other words, and with this, I come to my conclusion. In other words, what we see here, and I find this is, at least to me, really quite amazing, that what we see is that and this is like now the last point here in the conclusions, that the processing of spectral amplitude and phase information in these networks is organized in distinct parallel pathways that purely emerge from the learning process. And this is somehow, I think, reminiscent of parallel pathways, for example, in our visual system. And just to emphasize this again, this is in no way built into the structure. This is just something that comes out of the learning process. And as I've also shown you before, we get this hierarchy of features. And now, very briefly, a look. So I think we can say that, yeah, maybe we have more or less achieved these aims that we started with. And now, very quick look into the future. So this was the situation back then. And of course, in the meanwhile, there are much more studies on this. And here, also Yannick Roy is here somewhere. And so if you want more information, you can look at this really great review of, I think in the meanwhile, I guess around 200 studies doing deep learning on EEG. And now, where can we go from that? And actually, I think it's really, really great that there are so many papers coming out. And I don't see really like a competition who's finding now the best network, because I think what we can do now is we can take these, let's say, studies and use this to define search spaces for automatic architecture search, which are methods to optimize whole architectures, like including numbers of layers and so forth, automatically. And now there are really very efficient methods for gradient-based AAS becoming available. And with that, I think this is really becoming a very, very powerful option to find, let's say, if this would be the optimal architecture, to find it within such a defined search space. And so this is something where we want to go now, and I think it will be really interesting to see what kind of accuracy gains we will be able to get with that. And now like my last slide, and also then to understand, if we move through this like design space, what is changing in the internal representations of these networks? Do we get different basis functions and so forth? So this is one thing that we would like to do for the future. And with that, yeah, so first of all, I want to thank my great collaborators in the computer science department in Freiburg. So everything of this is really a very, very close collaboration with Frank Hutter, Joschka Böteker, especially for the deep learning part, and of course my group and funding. And thank you for your attention.
Thank you very much for the talk. I guess we have time for one or two questions.
Thanks for the talk. I wonder how you define phase-sensitive units in the network. Can you elaborate a little bit on that?
So it's basically the same perturbation-based approach. So we FFT the signal, and then in the phase domain or in the frequency domain, we can change the phase, or we can perturb the phase part, and then we inverse FFT the signal back to the time domain and use it as an input. So basically, it's really the same concept like for amplitudes. You just have to deal with, of course, with the circular nature of phase, but it's basically just a perturbation of the frequency domain signal.
Another quick question?
Thank you for your talk. It was very interesting, informative. I'm curious about one thing. You've decided to use a convolutional neural network for movement decoding, but there is an opinion that it's anticipated to give better results for P300. So what do you think about it?
Yeah, so the P300 would be a very good example of the second category. I mean, it's somehow probably related to the ERN. So, there are actually several studies also out there that already applied it to P300. So we have not applied our architecture to P300 data, but this would be really interesting to try out. I'm quite optimistic that it will work, yeah, not too badly, and just because it's a very similar problem to ERN decoding, and yeah, so it would be really interesting to try. You're right, yeah.